All right, hi everybody. This is the third quick video about what's going on in terms of conditional probabilities. We've kind of worked with conditional probabilities already, but we're going to talk about them a little bit more in depth, a little bit more formally here. We talked on Monday and Tuesday about playing cards. I just wanted to kind of make sure that everybody was clear on what was going on with these. So basically, there's 52 playing cards. There's 13 clubs of each suit. The suits are over here. We have clubs as a suit, diamonds, hearts, and spades. Obviously, spades and clubs are black. Diamonds and hearts are red. Then we have the different numbers of the cards. This is an ace or one, and just for technical purposes, this could be low or high, and then sometimes in blackjack it's 11. Then we got twos, threes, fours, five, six, seven, eight, 9, and 10. And then we have jack, king, and queen. These are also known as face cards because they have people on them. So jack, queen, and king are face cards. And this is the typical ranking. Sometimes, like I said, you could put the ace down here. There's 4 of each card, 1 of each suit. And so you can kind of use this as a reference for some of the probability questions that we'll be asking later on. So for conditional probabilities, we have a formula. And the formula starts off with this notation right here. It says probability of B given A. This line right here means, means given. So knowing that A has occurred, what's the probability of B? That's essentially what we're asking. Formula of such is this right here. Probability of B given A is equal to the probability of A and B occurring. Remember, the upside down U is the intersection, that's and. Probability of A and B occurring over the probability of A occurring. We can flip it around and get this here. So these are not necessarily equal. They sometimes can be, but they're not always equal. And that's kind of what we're looking at. Now, we are going to just do a quick example here. For example, I could say, what's the probability of king given that the card is red? Now, if you think about this, you're going to say, okay, well, what's the probability of king and red card over the probability of red? Well, how many red kings are there? Let's go back here. There's 2 red kings, the king of diamonds and the king of hearts. So if I do that, it's 2 out of 52. And how many red cards are there? Again, going back, there's 26 red cards. So it's 26 out of 52. And 2 out of 52, or 26 out of 52, is 2 out of 26. It's really helpful when the denominator at the top and the denominator at the bottom are the same. And then we can reduce that to 1 over 13. Now, the question is well, what's the probability of a king? And the probability of king is 4 out of 52. There's 4 kings, 52 cards out of the deck, and that reduces to 1 out of 13 as well. Now, one neat thing that you can kind of see here is that the probability of king given red is both equal to 1/13, which is also the probability of king. So what can we say? Well, now, based on this knowledge, we can say king and red are independent. And the reason being is if I know that the card is red, it does not change the probability it's a king. It's still 1 out of 13. And so knowing that one thing has occurred does not affect the other. And this definition right here helps us determine when things are independent or not. And it also helps in showing that they're independent or not. So if I was asked, are king and red independent? This is what I would have to show. First, king given red is 1 out of 13. Then the probability king is 1 out of 13. And then they are equal. And that would be how we would show if they are independent or not. So let's use our new knowledge to see if we can do a couple practice problems here. I'll do a couple of these, and then you can fill in the rest. So first question says, one card is drawn. What's the probability? Is ace or red? So probability of ace or red. Well, knowing our addition rule, that's probability of ace plus probability of red minus probability of both. So ace is 4 out of 52, red 26 out of 52. How many red aces do we have? 2 out of 52. And so that would get us 28 out of 52. 28 out of 52, I believe, is 0.5385, thereabouts. You need to round to 4 decimal places on the quiz that you're going to take. So make sure you do that. 2 cards are drawn without replacement. That means we do not put them back. All right. So what is the probability they're both aces? So probability of 2 aces without replacement. Well, probability of the first ace is 4 out of 52. And then, because we're doing another trial, we're going to multiply those probabilities together, and there's 3 aces left out of the 51 cards. And so here we get 12 over whatever 52 times 51 is. And I believe this is 0.0045. And then it says extend the probability of getting 5 hearts in a row. Well, again, you're going to start, we got, let's see, 13 out of 52 for the first one, times 12 out of 51 for the second one, 11 out of 50 for the third one, 10 out of 49 for the fourth one, and 9 out of 48 for the fifth one. And when you multiply all of those together, you get 0.0005. And then these last 2 down here, it says, I draw 1 card and look at it and tell you it's red. What is the probability it's a heart? Notation-wise says heart given red. All right, so that's the probability of heart and red over probability of red. Probability of heart and red. How many red hearts are there? Let's see, there's 13 out of the 52. How many red cards are there? 26 out of 52. So that's 13 over 26, or 1/2. And then if we go back and we say, all right, well, what's the probability of red given heart? Well, one would think it's about the same. So let's just try it out. Heart and red. It should be red and heart, but it doesn't matter. Over probability of heart. So red and heart, that's 13 out of 52. Probability of hearts. Well, there's 13 out of 52, and then that's equal to 1. These aren't equal. And that is a perfect example of the conditional probabilities not being commutative. So we need to make sure we always check them out as best we can. And then this is now when we're talking about what happens if things are independent, mutually exclusive, or both, or neither. And so we have a couple rules. Obviously, if probability of A given B equals the probability of A, then they're independent. If the probability of A and B equals 0, then they're mutually exclusive or disjoint. Now, if something's mutually exclusive, it can't be independent. And if it's independent, it can't be mutually exclusive, but it can be neither. So if we're looking at red card and spade, let's see, probability red and spade. Is it possible for a red card to be a spade? Chances are no. Because of that, it's mutually exclusive. All right. How about red and ace? Well, yeah, we have red aces, so it's not mutually exclusive. So we got to kind of cross that off. Red and ace does not equal 0. It actually equals, actually, let's do this the right way. How many red aces do we have? We have 2 out of 52, which is not equal to 0. So it's not mutually exclusive. So now the only question is it independent? So let's say probability red given ace. It doesn't matter if we go ace given red or red given ace. We'll use it to check. Probability red and ace out of probability of ace. So red and ace is 2 out of 52. Probability of ace is 4 out of 52. And that is 2 out of 4, or 1/2. Now, what's the probability of red? Well, there's 26 red cards, 52 in the deck. That reduces to 1/2. Sorry. And 1/2 equals 1/2. So, therefore, they are independent. All right. Now let's try the last one. Face card and king. Are face cards and kings, can we both occur at the same time? Sure. Probability of face and king. Well, there's 4 face cards that are kings, so 4 out of 52 does not equal 0. Not mutually exclusive. So let's do probability of face given king is, let's see, 4 out of 52. That's probability of face and king over probability king. Well, there's 4 out of 52 there as well. So that's equal to 1. What's the probability of face card? If we go back 1, 2, let's see, there's 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12. There's 12 face cards. So that would be 12 out of 52, which is some number, but it's not equal to 1. So therefore, they're neither independent nor mutually exclusive. So I hope that helped. Good luck with some of the homework, and do that quiz for Monday, and we'll see you soon.